Hopefully this is recording, but it doesn't look like it is. There it goes.
I tried to open it and it said in here for a long time when I go.
Okay. Oh, that was you? I didn't get home until like 10:30 last night. I never text people back. Oh, you did?
30 minutes ago. Yeah.
Oh, I was upstairs in the lab, remember? I told everybody I would be in the lab from noon to 1.
I knew that. I knew
Right.
that.
So you could have actually walked up and asked me the question. Okay, anyway, so in the lab we're going to start talking about this. And there are 4 topics we're covering that all revolve around homeostasis. Most of the very first section is actually review. In fact, I can't even think of what's not review. This is not review. The concept's review because we keep talking about it over and over and over again. Stable balance means what you put in, you get out. What's that called? Homeostasis. What you use up, you have to replenish. When you cool down, you have to warm back up. When you get too hot, you have to cool down. That's all homeostasis, and that's stable balance. That's the point of homeostasis. If your inputs exceed your output, we call it positive balance, which is not always a positive thing. We call it positive balance because your gains exceed your losses. What if you're gaining more heat than you're losing? What's going to happen to you? You're overheating, you're going to cook, and you're going to die. I found yesterday somebody made a comment about that over at the other school that I teach at. They said, you say that you're going to die a lot. Oh, I'm just trying to put the fear of God in you, right? So don't get too hot or you'll die. And then I watched Return of the Jedi last night, and the Emperor says, you'll die, and I'm like laughing inside about it. So negative balance means you're losing more than you're gaining. Think about calories. If you're losing more than you gain, what are you doing? You're losing weight. Is that always a good thing? No, it can be a bad yes. No, it can be a bad thing. Right? Think of anorexics. They actually burn more calories than they take in, and they're putting themselves in a life-threatening situation. So you need to know those terms.
So positive is gaining more than you lose.
Positive is gaining more than losing. Negative is losing more than gaining. These fluid balance sections, like I said before, I'm going to skip through it right now because we talked about it in the lab, but we've actually talked about it already, almost everything in here. So when you look at the compartments for fluid, we've talked about it. 60% of your body is made up of fluids. You know the extracellular and the intracellular. You should know what ions are most abundant in those 2 areas. So what's inside? What's the most powerful ion inside of a cell? Inside of a cell. Potassium. In the extracellular fluid, it's sodium. We've talked about the concept of volume and pressure. What did I tell you about volume? When it rises, what can you count on happens to pressure? Yep. So when your blood volume rises, your blood pressure goes with it. When your blood volume goes down, your blood pressure drops with it. Yeah. We've talked about this pathway of how you fix things, the baroreceptor reflex, which goes to the medulla oblongata and regulates things. I'm going to jump ahead. Like I said, we talked about this in lab. We talked about the kidney already. We talked about the chemicals. We talked about hyper and hypotonic. And then this I'm going to talk about again. Yep.
All this we talked about.
So when fluids move into the interstitial from which side? From plasma to the interstitial.
Yeah, and then
Yep.
only so much moving.
It will keep moving towards equilibrium. It's just moving slowly. So if you have, and how's it moving, by the way? How's the fluid moving? By diffusion. So if you have high volume of blood, let's say that you ate a bag of pretzels. I'll wait for everybody else to get done talking. So let's say you ate a bag of pretzels, right? And now you have hypertonic blood. You're going to drink water to balance that out, right? So now suddenly your blood volume did what? It increased. And what's the symptom that comes along with that? You feel bloated, right? The reason you feel bloated is because now you have a lot of blood volume. If you have lots of blood volume, what do you know about your blood pressure? It's high. Where's that pressure going to push water? To the interstitial fluid right away, right? So that short-term regulation is going to push it to the interstitial fluid, and now that volume rises, right? Which is the signs of swelling. But what's the next thing that's going to take that fluid? The cell. Because as that water level rises, it's going to start pushing into the cell, and what's going to happen to the cell? It's going to swell up too. So, and then as you start urinating a lot out, what happens to the blood volume? It goes down. What happens to the interstitial fluid? It goes down into the blood, and then what's going to happen to the cell's fluid? It goes to the interstitial fluid. So it's constantly between those 3 compartments going back and forth by diffusion. Yep. the edema is because the tissue itself is swollen. The lymphatics can't keep up with clearing it away. That's all of the above. Yep. Okay, acid base, and we talked a little bit about this in the lab too, but for the people that haven't seen it yet, I'm going to talk about it. Acids, when you see an acid, it's something that liberates or frees up a hydrogen. And the hydrogen has that little positive sign because if you know anything about chemistry, when you look at hydrogen, it's the smallest atom out there. It only has one thing. It has an electron. And that electron carries a negative charge. So when you take its electron from it, what's it leave it with? Positive charge. That's why they put the positive up there, is because someone has stolen the electron from this item. If that's the only thing that belongs in the world, is it happy? No, it's ticked off because you just stole its electron. So what's it going to do? It's going to spread the hate. Just like you. If you come into class angry, what are you going to do? Spread the love or spread the hate? Hate. You spread the hate.
Haters.
Haters, yeah. So you make everybody else's day bad. That's what hydrogen does. When somebody steals its electron, it goes around and destroys or damages everything it possibly can. Like proteins. What's it going to do to proteins?
Take their electrons.
It's going to try to take their electron. What's it do to them? I was hoping you'd remember this, but it denatures. Why does it denature? Remember when we talked about the stomach? Hydrogen ions, acids, denature proteins. Do they digest them? No, they just denature them. They warp them. They beat them into a new shape. They're so angry. If you take acids and you take albumin from an egg, that clear part of the egg, and you put it in acid, it denatures it. It changes its shape so light doesn't move through it as well, which makes it cloudy, which makes it look what to you? White. Same thing with albumins in your blood. If you have too many free acids in your blood, it will change those albumins in your blood, change their shape, and they don't work properly anymore. The proteins you really want to worry about are things like enzymes, because enzymes speed up chemical reactions so that you can carry oxygen, so that you can move carbon dioxide efficiently, so that you can move cholesterols and steroids, and if those things don't work anymore, you can't move any of those. You can't change them. So then you would die. And then bases. Bases usually carry an extra electron. So they're carrying around an extra teddy bear, right? So they find in hydrogen, and what do? They share. How does that make the hydrogen feel? Less angry, right? So the hydrogen is now happy. It's contempt. It doesn't have to worry about making things different. So if I take a base and I add it to an acid, what's it do to the acid? It neutralizes it. Yep. It takes the angry component away from the acid and makes it happy again. So bases, what they do is they bind to acids. They satisfy an acid, is another way you can think of it. Right. So here's an example of an acid, a strong acid. If I take a strong acid and I put it in water, they say it dissociates fast. It splits. So if I take something like hydrochloric acid, where did you hear about that at? Stomach. If I take hydrochloric acid and I put it in watery solution, it dissociates. That angry acid, that's the only thing it had, it's lost its electron, now it's going to go around and damage things. All of the hydrochloric acid you put in your stomach dissociates. So you have all these free acids looking to hurt things. If you take something that's weak, like carbonic acid, that long equation I keep showing you over and over again, that CO2 plus H2O makes carbonic acid. What's carbonic acid do? It'll dissociate into acids and bases. In this situation, it dissociates into a free acid, and what's the base? Bicarbonate. Yep. In the same situation, this acid's really strong, this base is really weak, so the acid's what you have to worry about. But did you dissociate all of it? No, you just dissociated one acid. This guy's going to be easy to take care of and neutralize. So a strong acid dissociates completely, and it's very dangerous. A weak acid only partially dissociates, and it's more mild. So when you're using that equation, you're taking CO2 plus water to carbonic acid. Carbonic acid's weak, so when it dissociates, these bases, the bicarbonate and the acid, are not that bad. But the problem is, what if you accumulate lots of this free acid? Let's say you're holding your breath for a long time, you're accumulating CO2, that equation keeps shifting over, and when it gets over here, it's making lots and lots of free acid. Is that bad? Very bad. What state do you fall in? Acidosis, which causes lots of problems. Okay, the pH scale. pH scale is a rating of how much acid is free in the solution. So if the acid and the base are in equal proportions in a solution, we rate it as a 7 on the pH scale. It goes from 0 to 14. 7 is perfectly neutral. That means there's just as many acids as there are bases, and they're perfectly happy. Water, pure water with absolutely nothing in it, is neutral. So distilled water. If you look at your stomach acid, it's about 2, way down here, extremely acidic. Why this is so important is that if your blood, which is, by the way, 7.4, if your blood is 7.4 and your stomach acid, which is right next to your blood, is 2.0, the number of times that is acidic compared to blood is extremely high, and this is why it does this. It's called the Henderson-Hasselbalch equation. I'll show it to you later, and thank God you won't have to memorize it. But no, not like the actor that drove the Knight Rider car. That's Hasselbeck? Hasselhoff, right. Thank you. The Hoff. So if you go from 7.4 just to 6.4, you've actually increased it logarithmically, which means by 10 times. So just going to 6.4, and yes, you would die at 6.4. At 6.4, you're a goner. You can't handle under 6.8. And it's because your blood is now 10 times more acidic than it was before. If you go from 6.4 to 5.4, now it's 10 more times. You're beyond dead. You're like rotting away. And so from 7.4 to 5.4, how many times more acidic would that be? That's 100 times more acidic. If you went from 7.4 to 4.4, it's 10 times 10 times 10, which is 1,000. If you went 7.4 to 3.4, it's 10 times times 10 times times 10 times times 10 times. That's 10,000 times. And if you go from 7.4 just down to 2.4, which isn't even as acidic as the stomach yet, it's actually 10 times 10 times 10 times 10 times 10, which is 100,000 times more acidic. Does 1 point make a difference? Very big difference. Yeah, just going from the wall of your blood vessel to the wall of your stomach, you've actually changed the acidity of that fluid by 100,000 times. If your stomach were able to penetrate and dump into your abdominal cavity, it would eat you from the inside out. Dangerous stuff. If you look over here, milk of magnesia, why do you take that? When your stomach is too acidic, right? When your stomach's too acidic, you take milk of magnesia. It's thick. It coats your esophagus. It coats your stomach. Why? Why is it so thick and coating your stomach? To try and neutralize the stomach acids that are irritating your stomach wall. And oven cleaner is extremely what? Is extremely right? It's extremely basic or alkaline. And I think I used this example in lab, but when I was younger, I used to rebuild Volkswagen Beetles. Loved it. It was fun. And to clean the parts, when I would rebuild it and clean the parts, I would use oven cleaner because it was so abrasive. It would actually peel all the tar and it would peel all the undercoating off the car, so I could refinish it. And if I got it on my fingers, it would actually make them really slimy because it's actually changing all of the proteins on my fingers. So whether it's a strong acid or a strong base, it's still extremely toxic. All right, so here's your blood, 7.4. If it's in the venous, the systemic veins, it should be more what? More basic or more acidic? Why more acidic?
In the vein?
In the vein. Why should it be more acidic in the vein? Because what else is high in the vein? CO2 is high in systemic veins, right? So if you have higher CO2, you have higher acids or more acids, which makes your pH more acidic. And then you have less CO2 in the systemic arteries, which means the pH is more basic. If you go beyond 7.35, so lower than 7.35, then you're considered acidosis. If you're above 7.45, it's alkalosis. And then there's your extremes. You don't live if it gets lower than 6.8. You don't live if it's over 8.0. Okay, fluctuations in hydrogen ion concentrations. Here are the primary things that you're going to see effects, like actual symptoms. So the first one is that when you become too acidic, it affects your nerves and your muscles. When you become too acidic, your nerves actually start shutting down. You start denaturing the proteins on the neurons, and they can't transport potassium, they can't transport sodium, they can't allow calcium to move back and forth. The neurotransmitters change. So if you're turning down the neurons, what physical symptoms would you see of this person's mental activity? They'd get slower. They'd get more sleepy. They'd respond slower. They're going to look like they're what? Like they're drunk, right? They're going to look like they can't respond. They're kind of drunk. They're kind of out of it. Their speech might start slurring. And then eventually they're just going to go, I just need to take a nap, right? Is that a good idea? No, because it means that their blood's so acidic that it's shutting their brain down. And then, of course, if it shuts down the medulla oblongata, what do they stop doing? They stop, right, living. I didn't say it, just for the record. They stop breathing, and then they stop living, right? So at the point where they get so, their brain shut down so much they're still alive, but you can't wake them, what are they in? A coma. Yep. And then if that's not correct, they die.
So when would you expect to see somebody's pH level who like a diabetic ketoacidosis?
It can vary, but you know it's not going to be beyond 6.8. So anything below 6.35, you're going to probably start seeing mild symptoms. Like they just feel kind of cloudy-headed, like they're not thinking straight maybe, and then as it gets worse, you're going to actually see them acting weird.
How could you induce this in somebody?
Why would you want to induce that
I
in
was just
somebody?
wondering like how you could make your pH.
I feel like if I tell you, then I can be held as an accessory for whatever crime you're plotting.
I was just
But
I see how you would think that,
ask
but no.
diabetics are the prime example because they're building up ketone acids, right? So they're building up all the acidic products, and then their brain starts shutting down as a result. Right? Just the opposite. If they become more alkaline, so they become more basic, it's going to be exactly the opposite. It starts causing irritability. It starts causing the neurons to start overfiring. You're going to see things like they feel really anxious. They feel, oh man, I feel uncomfortable. They're not tired at all. They're really uneasy. They're like anxious feeling. They might start hallucinating because these neurons are firing. So have you ever blown up a bunch of balloons really quick? You're getting plenty of oxygen, but what are you doing? You're losing CO2, which means you're losing acid, which means what's staying behind in your blood? Bases. And because the bases are so high, you're becoming alkaline. Have you ever blown up so many balloons that you actually start seeing stars?
Yes.
You're hallucinating. So it's overfiring the neurons and it's causing these little auras, and you're like, oh, if you pass out, it's because you became so basic. You don't pass out because you're low in oxygen. You're actually high in oxygen, but you're very low in CO2.
So you
And then-
actually could accomplish that because the more acidity,
Accomplish what?
What I was trying to say, like if someone were to try to do this to themselves, it could not be accomplished because once you start to get there, you would start hallucinating, you start feeling weak, and then you just like pass out, and then everything would equilibrium anyway.
For which, what are you talking about?
If someone tried to make themselves like eat a bunch of
Oh, like a
berries
kid
and
that holds their
become,
breath
like,
until they're blue in the face and they pass out? Is that
Yeah,
kind of an
like-
example?
or like
So yeah, as soon as they pass out, then they start breathing normally again and
or
everything's
like if
fixed.
someone tried to digest a bunch of like, I'm gonna eat a bunch of batteries and like throw off my pH balance. Well, you're gonna like pass out and throw up the batteries and then it'll go right back. So there really is no way.
I'm
to
always
do
glad
that.
you're in the front row, Megan. Thank you. So you always keep life interesting. I'm saying that in a nice way. I'm just thinking, who the hell eats batteries? The whole time you're saying that, I'm like, who would eat the batteries?
Yeah,
Huh,
that's
who?
what I mean. That's
Oh,
what I mean.
people with, like,
there's no
pica
way
and
to
stuff?
physically do this to yourself because your body will fix it somehow.
Well, eating batteries, you can vomit it back up, but yeah. Okay, moving on. So anyway, it starts shutting things down. So think about it. When your muscles are becoming too excited, they start getting twitchy. But if they become too depressed, you actually start becoming paralyzed, right? So think of the neuron activity, the muscle activity when you go into an overexcited state because you're very alkaline. You start getting twitchy, you start getting excited. If those neurons start overfiring and they actually seize up, what do you have to worry about this person not doing now? I was so waiting for someone to say living, but right, they stop breathing. If they stop breathing, then they stop living, right?
Do people who are bipolar that take a lot of lithium, do they have too much acid? Or why is it so toxic?
It builds up in their brain. Yeah. Okay, number 2, influence on enzyme activity. So enzymes, I already talked about this. When you start changing the pH, we talked about this in digestion too. Salivary amylase works at a pH just slightly acidic, just slightly, barely. So it's like 6.8-ish. If you put that in the stomach that's 2.0, what's going to happen to that enzyme? It's a protein, right? So what's going to happen at that high acid? It gets denatured. It doesn't work anymore. If you denature a protein, it doesn't do what it did before. Right? So it gets denatured and it doesn't work. If you change an enzyme that's in the blood, like carbonic anhydrase, that helps you convert CO2 to carbonic acid, blah, 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 if you change that enzyme, you can't convert the CO2, you can't change things, you can't move oxygen, you can't move carbon dioxide, and you can't live well. So enzyme activity, when your pH of your blood starts changing, it starts shutting off the enzymes that normally work at what pH? 7.4. And then influences on potassium levels. What you really want to think about with the potassium is, by the way, can you get too much potassium?
Yes.
Yeah, if you get too much potassium, what organ's going to start shutting off? Your heart. We talked about that in cardiovascular. So if you're building up an H plus ion and it's too much, your body's actually going to try and kick that H plus out. But if it kicks a lot of pluses out, it becomes electrically unstable. So what's it have to either bring in or kick out with the H+.
Bring in plus or kick out minus.
It has to bring in the plus or kick out a minus with it. So if you become too acidic, what happens to your potassium levels? They start, if you're too acidic, you start pushing out an acid and you have to pull in a potassium, right? So pull in the potassium. If you're too alkaline and you start pulling in lots of hydrogen, H+, you want to do what with potassium? Push it out. So hydrogen ion levels have a direct effect on potassium. And when you go on beyond this, like when you get in pathophysiology, you'll see that things like insulin, calcium, hydrogen, all these things, glucose, they actually have a huge effect on potassium levels. It's not just potassium for the sake of potassium. And no, if you eat a whole handful of banana or a whole bushel of bananas, your potassium doesn't spike and kill you.
So if you kick out hydrogen acid, potassium comes back in, or does it go out with it?
If you kick out a hydrogen acid, you bring in the potassium as an exchange. Because as you're taking away a positive, you would bring a positive the other way to keep it balanced. They're both positives. So if they both move together, you're double losing positives, so you need to move them opposite to each other. Does that make sense? If you're in what? If you're in acidosis, your hydrogen ions are high, so you're going to try and isolate those potassiums and put them somewhere so they're not in the blood. And you'll actually put them in cells. It doesn't have to be urinated out; it'll be put in the cells. Pathophysiology is where you're going to learn more about this. You're going to kick out a potassium. Potassium has nothing to do with the base. So if you get rid of a hydrogen, you're changing your acid level, but you're actually making if you're kicking out a hydrogen, you're trying to take acidosis down, but you're bringing in a positive charge to balance the electrical activity out. Does that make sense? pH and electrical are two totally different things. So what you're doing is you're trying to get rid of the acid to regulate your pH. In exchange, you're bringing in an electrical charge, which has nothing to do on pH, to keep the electricity neutral. See how they're two different things? Oh, sorry, I was pointing over your head this time, but... When they go into acid, it is harder because as soon as they start changing their insulin has a huge effect on potassium too, which is where pathophysiology comes in. Diabetic ketone acidosis is a disaster. My piece of advice, don't become diabetic. It's a mess, right? So as soon as you start changing things like ketone bodies in the body, it starts changing the acidity of the body, which the acidity changes the potassium, which potassium is going to affect insulin, and insulin is going to come back and re-affect the acid and the potassium. So you don't have to know this, by the way, for this class. You just have to know potassium. If a patient's constantly coming in with acidosis, they need to regulate their blood sugars better. It's because they're not regulating their blood sugar that they keep coming in with that. Yeah, Megan?
So what we need to know...
By the way, this is the last question for this because we're getting way off of
all
potassium.
really confusing. So going from the acid-base balance in the beginning of the notes to where we are right now,
This is all about acid and base. So where we're at right now is that hydrogen ions need to be regulated in your body for several reasons. They need to keep your neurons functioning properly, they need to keep your muscles functioning properly, they need to keep your enzymes in your blood working properly, and they need to keep your potassium levels proper. Is everybody with that so far? If you change those, nerves don't fire properly, muscles don't fire properly, your heart will not work properly, potassium, and your enzymes won't work properly, which means you can't move things like oxygen and CO2. Does that get everybody back on the same page?
Yes.
Okay.
There's a balance between...
There's a balance that you have to stay.
You
Yep.
have to stay in. Homeostasis, got it.
Cha-ching. Okay, and then how do you make hydrogen ions? So the first place is this mechanism we keep talking about over and over again. When I see this, I always draw the bathtub. Here's one thing I want you to put by the bathtub. Over on this side, what organ regulates this? The lungs. So on this side, if the lungs are failing, it's going to screw this side of the equation up, right? Over on this side, right kidney. There are two major organs that regulate your acid-base balance. Guess what they are? Lungs and kidney. If one of them fails, it pushes the weight on the other one. So if my lungs fail, what organ in my body has to take over and work really hard? The kidney. If I'm holding my breath, what happens to my blood? Think about the pathway we've talked about. If I hold my breath, I'm retaining what? CO2, which makes me retain acid. So if I'm holding my breath, it's the lungs that are broken here. What does the kidney have to do? does it have to make you keep more acid or get rid of more acid? Get rid of more acid, so what's going to show in your urine? Very acidic. Yep. So just think of that pathway going through here again. Let's say I'm breathing too much. I'm losing too much CO2. The lungs are broken, right? What's my blood doing? I'm losing lots of CO2, so I'm losing lots of acid. So what's happening here? I'm becoming very basic. What's the kidney going to stop getting rid of? Acids. It's going to try and keep the acids, but what will it start getting rid of? Bases. What's the base that you think it's going to get rid of? Look at the equation. Bicarbonate. Everybody with me? Okay, and these are things we've already talked about before. I just added the kidney to this side of the equation. All right, the second thing, inorganic acids produced during the breakdown of nutrients. So when you're eating and you're breaking down primarily what, if you've been in lab? Proteins. So when you break down proteins, you're making lots of acidic byproducts. If you eat a lot of protein, if you're on the Atkins diet, what can you expect to happen to your blood? Becomes more acidic. So what can you expect to happen to your urine as an output? Becomes more acidic also. So just by the breakdown of some foodstuffs, you're going to add acid to your body. What if you eat a lot of breads that are full of sodium bicarbonate? What would happen to your blood pH? It'd become more basic. Yeah. So I'm not just pointing fingers in one direction or the other. It's if you take in too many things that make acids, you're going to become acidic. If you take in too many things that are basic, you're going to become more basic or alkaline. And then this last one, intermediary metabolism, is referring to what you do with carbs, proteins, and fats once they're in your system. So once you've absorbed them, they get into your bloodstream, now you're going to change them and manipulate them with organs like the liver. The liver is going to take sugar and do what with it? If you have too much sugar in your blood, the liver does what? Pulls it out of the blood and stores it. Do you remember the storage form of sugar? It's glycogen. Yep, so it stores as glycogen so that when you're sleeping for 8 hours through the night and you're not eating, you can slowly break the glycogen down and put it back in your system. Glycogen is an awesome source of energy because it doesn't make a lot of waste product when you metabolize it. But when you run out of those sugars, no, the moral of the story isn't to eat a lot of sugar because anything extra that you don't need gets turned to what? Fat. Yeah. So I love it when I see candies that say a fat-free product. But if you eat the whole damn bag, it doesn't matter because all that extra sugar is turning right to fat anyway. Anyway, and then when you start breaking down things like proteins and fats, because you're out of sugars in your body, they make metabolites like acetone, which is a ketone body. Yeah. So this intermediary metabolism makes things like ketone bodies, which are very acidic. And that's where this comes into play. So after you run out of sugar, when you start breaking apart proteins and fats, you make ketone bodies, which are acidic. Right? 3 lines of defense, you absolutely have to know these. In order, as soon as you make an acid, the first thing to try and neutralize it, which by the way, neutralizing an acid is referred to as buffering it. Neutralizing a base is referred to as buffering it. Can you get too much base in your system? Yes. Remember oven cleaner? Not a good idea to drink it. So if you get too much of either of these, acids or bases, the first thing that happens is that you get this buffer system that will try to neutralize them. And the first thing that happens is a chemical buffer, and it literally works at the level that the acid is being made of. So it's the level of the cell, typically. As soon as you make an acid, boom, you neutralize it. When we talked about red blood cells, as soon as you make an acid from that CO2 plus H2O is carbonic acid, and then it frees up to acid and bicarbonate, right there in the red blood cell, we actually buffered. We took that acid and stuck it to the hemoglobin, buffered. We took the bicarbonate and we shifted it out into the blood, and it stuck to acid, buffers. So we're trying to neutralize it. This is milliseconds. As soon as you make the acid or base, you neutralize it. The second one, if this isn't working and you're making too many acids or too many bases, then what happens to your breathing? Either speeds up or it slows down, depending on what's going on. Why would it speed up? You're trying to get rid of CO2, so what state is your blood in? Acidic. If you slow down, what stage is your blood in? It's basic, because you're trying to retain more CO2 and retain more acid. Everybody with me so far? Yeah.
Okay, so medicines that make you breathe slower, like the antidepressant or even some painkiller, does your kidney have to...
Your kidney has to try and clear that crap out. But the point you brought up perfectly fits here. If you take a bunch of drugs that slow your breathing, like because you overdose, not because it was an actual drug that literally would slow your breathing, but like say you overdose, what property is that drug? It's very basic. So when you take drugs that are coated in bases and somebody overdoses on those drugs, they're getting a lot of base in their system. Why are they slowing their breathing? to try and retain CO2, which retains acids to neutralize those bases, is why they slow their breathing. So when they've overdosed and they start breathing slower, that's why. Unless it's a specific drug that actually worked like on the central nervous system to slow their breathing, like opiates. Opiates actually slow respiration, which is a totally different category that has nothing to do with this.
Okay.
Is that what you were asking? Like an opiate?
Yeah, like an opiate, because you can definitely tell.
Yep.
if they're on it.
Opiates, they slow down respiration rate. So when people take a lot of opiates, it slows their breathing, but it has nothing to do with acid and base. It has to do with them basically stopping that neuron. Remember when we talked about neurons and pains and how opiates inhibit neurons? That's what it is.
So it doesn't affect humans, it just works out else.
Yeah.
So
Okay,
the
so-
people that OD'd, like Heath Ledger or whatever, couldn't they just pump a bunch of acidic nutrients in him?
I think they found him dead, didn't they?
Okay, but like, if he was still not dead.
If somebody had overdosed on something, they would check their bloods and they would handle that appropriately. So if they had too much base or too much acid, because it depends on what you take, so it can change a lot. But that's all for your clinical stuff.
Yeah, true.
Okay, and then next. So if the lungs aren't working properly, what's the next organ that has to kick in? The kidney. And they go in this order. Chemical right away within milliseconds, respiratory within minutes to hours, and the kidney within hours to days before it'll actually fix the process. Think about it. Your respiratory versus renal, what do you do more often, breathe or pee? I'm counting on breathing, right. So here, you're breathing more often, so it's going to be a faster regulator of acid base, where the kidney's a lot slower. Okay. And then I have this up here a few seconds. The chemical buffer should fix it. You have to know these 4 chemical buffers. What you have to know about them is where they work also. It's super important. So the first buffer is called the carbonic acid bicarbonate buffer. This is because carbonic acid and bicarbonate, they are the fire extinguishers or the neutralizers. So if you're actually making carbonic acid, you can't put out carbonic acid with carbonic acid. It doesn't make any sense. So this will actually buffer anything that's not made from carbonic acid or bicarbonate. It's any other acid base that's not those things. And I keep saying that over and over again because I'm trying to stress this word, buffered from non-carbonic acid. Where it happens is in the extracellular fluid. So in the plasma, and it will also be in the what other fluids, the major area? Interstitial fluid.
What's an example?
That's where it's made.
If you eat a starchy substance and you broke that down and you broke it into bicarbonate, the bicarbonate would actually that is a bad example, isn't it? That's a good example. Oh no, that actually is a good, because that's intermediary metabolism. That's not from that bicarbonate carbonic acid pathway that we keep talking about, which is CO2, H2O, carbonic acid, and then sodium bicarbonate. That's from intermediary metabolism, something totally different. Did that make sense, or just still confusing? See this down here? If it works in this pathway, this doesn't work on it. Does that help? Yeah. And then when we get here, I'll show you another example. So this is in the extracellular fluid for anything that's not because of this system down here. And then number 2, the protein buffer system that's intracellular. Where's it at? Inside of the cells. Inside your cells, you have those protein anions. What are they made out of? Anion or proteins. What's a protein made out of that you have to break it down to digest it? Amino acids, which tells you on one side it's amino, which is basic, and the other side is an acid. They're long chains. They're like Legos. There's always a top and a bottom. No matter how long you make the chain of Legos, there's still the top and the bottom. One side's got to be acidic, one side's got to be basic. If a base comes in around this protein, where's it going to stick to? Boop, the acid side. If an acid comes in, where's it going to stick to? The base side. So it can neutralize both of them, or it's a perfect buffer. A protein is an awesome buffer because it has part amino and part acid. It can stick to either one. This one breaks down or neutralizes anything that's inside the cell. It doesn't break down amino acids. It uses amino acids as proteins to neutralize other things. So this is intracellularly, where the last one was extracellular but non-carbonic acid. The third one is the hemoglobin itself. So when you look at the hemoglobin buffer system, it's actually buffering things that are made from this pathway. Remember, we hold our breath, it adds to water, turns into carbonic acid in the red blood cell, and then in the red blood cell it frees up to acid, sticks to the hemoglobin, and then this bicarbonate gets shifted out of the cell. When the bicarbonate goes out of the cell, by the way, what comes into the cell? We call it the shift. Chloride. Yep, it's called the chloride shift. Why did chloride come in as bicarbonate was leaving. Because they're both negative. As you bring one negative in, you need to get a negative out to keep it electrically neutral. Right? And then this little thing up here is the actual, this is the acid, it sticks to a hemoglobin, and now it's neutralized. There's no charge over it anymore. So this is the process that's happening primarily in red blood cells. And then number 4, the phosphate buffer system is an important urinary buffer, so it's happening in the tubule walls. So this is happening because of the tubule walls. And this uses phosphate, and phosphate will actually stick to hydrogen and neutralize it. Phosphate has a negative charge over it, so what's it like to grab a hold of? Positive charges. So the key here, where is this first one working? Yep, so the plasma and the interstitial fluid, when it's what? When it's not this thing back here, right? This one is revolving around hemoglobin, so it's primarily where? In the red blood cells. This one's inside of all of the cells, and this last one is primarily where? Inside of tubular walls. So here you have the tubule wall, and you can see you filter the phosphate, and then the phosphate will kick out. The phosphate will bind to one of the hydrogens that is excreted from the tubule wall. That way it binds it up, it holds on to it, and it keeps that hydrogen safe. It's almost like this phosphate's on a kamikaze mission. It finds a hydrogen, grabs a hold of it, and then it's pushed down into the urine and excreted from your body. And then they start separating, and when they separate, then it makes your urine a little bit more basic. Kamikaze mission, yeah, I can't think of another
So what we
example.
need to know is where they are.
Where they are and what their primary thing they're chewing. Like a question like this. If a hydrogen ion's made from carbonic acid, where's it buffered? It's in the hemoglobin, right? It's in the red blood cells, so it's got to be the hemoglobin. Yep, that was a fast answer. I must have really pushed that one. So if it's made from carbonic acid, remember, this one, not from carbonic acid. Here's your carbonic acid right here. So it's in the hemoglobin. All right, next one. So respiratory system. If those 4 systems didn't work, now it depends on the lungs. So it takes a few minutes before the lungs will start doing this. And then the lungs depends on this process. The lungs will do everything around this side of the equation. So if you become too basic, what's the lung do? Does it breathe harder or does it stop breathing? If you're too basic, it stops breathing to build up this, which shifts this equation to the right to make more acids. If you're hyperventilating, you're breathing way too much out, you're blowing out too much CO2, right? That was a bad example. But if you're blowing out too much CO2, what's your body starting to become? Basic. What's the organ that's going to have to fix that, by the way? Kidney. Yep. So what if your kidney's not working and you're retaining lots of acid? What's your lung going to have to do? It will have to blow out more CO2. So then you're going to start breathing your deeper breaths. Faster and deeper, trying to get that air out. And then if that pathway doesn't work, then the kidneys have to come in. Kidneys are the slowest. When we talked about what the kidneys can do with hydrogens, can the kidneys reabsorb hydrogen? No. Can they secrete hydrogen? Yes. So the kidneys are going to secrete hydrogen if, why would they want to secrete hydrogen? If you're too, why would they want to get rid of hydrogens? If you're too acidic, they get rid of hydrogens. If you're too basic, can they reabsorb? No. What do they do to secretion? They stop secreting, right? So if you're too acidic, you can actually secrete the hydrogens, but if you're too basic, all you can do is stop secreting. Right? And then bicarbonate. If you're too basic, what are you going to do with bicarbonate? Your kidneys are going they going to keep it or get rid of it? They're going to get rid of it. You can actually excrete the bicarbonate. You can secrete the bicarbonate. If you're too acidic, what do you want to do with the bicarbonate? You want to keep it. You can reabsorb bicarbonate. So these two are actually really different. This one you can both secrete and you can reabsorb, but this one you can only secrete, right? Or stop secreting. So here's a pathway. If my plasma acids get too high, what state am I falling into? Acidosis. Yep, so at the same time, remember your CO2 is going too high. So if my acid's getting too high, what can my kidney do with the acids? It can secrete them, right? So it increases secretion. As you increase the secretion, what actually happens to the number of acids in my plasma? They go down to help bring it back to normal. What else can I keep to help neutralize acids? I can keep bicarbonate, which brings my free acid level back down. So both these situations, they're trying to reverse this high acid. One is by getting rid of it, urinating out acids. The other one's by bringing in bicarbonate to neutralize those acids in my blood. So remember, filtration, you can filter acids. Can you reabsorb them? Nope, but you can also secrete them. So if I put 100 acids out here, but my blood's too acidic, then I can put another 100 out by secretion. Now I have 200 that go into the urine. And this is kind of a complex process, but I kind of showed it to you a little bit when we were talking about digestion before. If I'm too acidic, I have too many acids here in my blood, I take the CO2 in my blood, I shift it across, and I use that equation, CO2 plus water makes acid. The acid's pumped out. Look what's brought in with the acid. Yep, as acid's being pumped out, potassium's being pumped in for what reason? To keep it electrically neutral. Yep, it's keeping it electrically neutral. This has nothing directly to do with the pH. Huh? That's over here. Yep. So the potassium, as you're pulling the potassium here, you can actually shift them back and forth too. And that's the sodium-potassium pump, which is a whole other process. Right? So you could potentially burn more energy and push more potassium out here to get it forced the other direction, but now what are you doing if you do that? If you're pushing potassium out, what are you also pulling in? Sodium. So is too much sodium bad for you? Yeah. And that's one of the tricks about the body, is the body has to constantly maintain all those different things all at the same time. It's like spinning plates in there. If you pay too much attention to one, another one's going to fall and break. Okay, and then ammonia secretion. So ammonia secretion is two important urinary buffers. We already talked about the phosphate. The second one's ammonia. This is interesting, and this deserves a star. This is probably the most confusing one, only because if I'm in an acidic state, what do I want to get rid of? Acids. If you secrete more ammonia, it's because you're in an acidic state, which makes it kind of confusing, because what is ammonia? It's a base. It's a very powerful base. So during acidosis, you're going to secrete ammonia, and you're going to push ammonia out in your urine because it's going to be on a kamikaze mission too to do what? Grab the acids and escort them out of the body. So when you're looking at this process here, so I have way too much acid in my body. I'm acidotic. I push the acids over here, but I take ammonia, and I also push ammonia with it to grab the acid. Would it be bad if I made a lot of acid and put it in my bladder? What does acid like to do?
Eat things.
Eat things. It would eat your lining of your bladder. So you need these phosphates and ammonias to do what to the acid so it doesn't kill you or eat a hole in your bladder, to neutralize it. So like I said, the kamikaze mission is to grab a hold of the acid and escort it all the way out of the body. Then they separate once they're out of the body. How do you know that? Because if you pee on something, or if your cat pees in the litter box, tomorrow it smells like ammonia. But a cat's an obligate carnivore, so what's it eating? Protein, which makes its blood very acidic, which means it actually urinates out a lot of acid, but what escorts the acid out? The base, the ammonias, right? So when the ammonias free up, it has that really toxic, nasty smell. Acid really doesn't have much of a smell typically.
So ammonia neutralizes acid?
Ammonia neutralizes the acid, and then when the ammonia and the acid go their separate ways in the litter box, then they start smelling like that. So like if you peed in your toilet and you didn't flush it for 2 days, how does it smell? It smells like ammonia, right? It's the same idea. There's your take-home experiment for tonight. Not until go home, pee in the tub. Yeah, there you go. Pee in the tub, leave the cork in it, and then Tuesday when you come back, tell me how it's smelling on Tuesday. Yeah. Do not flush. Yeah. If it's brown, flush it down. If it's yellow, let it mellow. Oh, yeah. I saw that sign on a toilet once, and I thought, no, I couldn't do it. Okay. Next major point: acid-base imbalances. What are the two imbalances? You either get too much acid, which is acidosis, and you get too much base, which is alkalosis. So we're going to subdivide those two. That equation I warned you about, the Henderson-Hasselbalch equation, that's it.
Wait, what?
I hate math, and I'm not going to push that kind of punishment on you, but this is why scientists and mathematicians should never hang out, because they make silly equations like this. But your pH is actually calculated by 6.1 plus the logarithm of 20 divided by 1, which is your bases divided by your acids. Nightmare. So the moral of the story here is your pH of your blood should be 7.4. The second thing you want to use as a take-home message is that what is this base they're measuring? Bicarbonate. And what's this acidic property thing? CO2 is carbon dioxide, right? So if you look at this equation, the CO2 represents the acid, the bicarbonate represents the bases. Are they perfectly proportionate? No. Which one's more powerful? The acid. When I look at this, I always think of a teeter-totter. If you took a teeter-totter and you put a pound of lead on this side and a pound of feathers on this side, which one's heavier?
Neither, they're both a pound.
I love how the room always gets split because people are like, I've heard this one before. They're both a pound, right? So they're actually perfectly level. They're both 1 pound. But if I put one little unit thing over on the lead side, what's going to do? Make the lead side pull down, yeah? It's going to take a lot of feathers to actually balance it back out. So when you look at acids, does it take very much acid to make you acidosis? No. Does it take a lot of base to make you alkaline? It actually does, yeah. So when you're balancing this out, you want to think of that equation that we've talked about a bunch of times before. Right now you're perfectly at pH, 7.4, perfect pH for the blood. If I start holding my breath and I stop breathing, what's going on? If I start holding my breath and I stop breathing, I'm gaining too much CO2, so it's pushing down on this side. What am I falling into? Acidosis. When they say that this equation drops below 20 to 1, they say you fall into a state of acidosis. The organ that's doing it is what they point a finger at. What organ was doing it? The lungs, so they call it respiratory acidosis. If it's any other organ that's screwing this up, they call it metabolic acidosis. It doesn't have to be the kidney, it could be anything. You could be exercising really hard, and what acid are you accumulating? Lactic acid, right? So it's metabolic. It's just not respiratory.
So there's
The reason
only
they-
two types of acidosis. You're
You're either respiratory or metabolic acidosis, yep. The reason they call this, say this dropping below 20 to 1 is, you can think of it this way. 20 divided by 1 is 20, right? If it goes below that, you're in a state of acidosis. So in other words, if I take this acid and I double it, what just happened to my equation? What's 20 divided by 2? It's 10. That's less than your original equation of 20, right? So if it drops below, if their math comes out to below 20 as an outcome, what state are you in? Acidosis. When you do this in a clinical setting, they'll take arterial blood gases. They'll take a sample of their blood, and they'll look at it, and they'll say that their CO2 is off the chart. It's really high. What kind of acidosis do they have then? Respiratory. If they said that it's because their bicarbonate changed, their CO2 is normal, but their bicarbonate's abnormal, and they still have acidosis, what do they have? Metabolic. So in this situation, you can have acidosis by changing the CO2 or by changing the bicarbonate. Acidosis because of respiratory means your CO2 got heavier, more CO2. If it's because of metabolic, it means your bicarbonate got lighter. You lost too much bicarbonate. Just the opposite, if you go into alkalosis, it means the equation went above 20 to 1. So there are two ways to do that. To make this higher than 20 as an outcome, I can raise the base, right? Too much base makes you basic, alkaline. So if I double this and now it's 40 to 1, what's my outcome? It's basic, it's higher than 20 because now the number's 40. If I do what to my acid, I can get basic. If I lower my acid level, the base becomes more powerful. So if I cut this in half, guess what the outcome is? If I take 20 divided by 0.5, this is what I hate about math. It's 40. It's still 40, right? So if you lower the acid, you become basic. If you raise the base, you become basic. If you lower the acid, which is CO2, what kind of alkalosis is it? What's the organ at fault? It's respiratory. Did you just say metarespiratory?
No,
I swear I just heard.
some of the-
Okay, so two people said it at the same time. I was like, wow, I've never heard anybody try and pull their way through that. That's like how you fudge it on a written part. Metarespiratory.
Okay, I answered the question.
Okay, and then all these things in your notes are actually breaking down just without the pictures. So the pictures are on here as a teeter-totter to give you a visual illustration, but the written form of this is that if you change the pH so that it's respiratory cause, if it's respiratory cause, it's because of what chemical? CO2, all right? If it's because of bicarbonate, it's what?
Anywhere else.
It's anywhere else. So if I ate a whole bag or a loaf of bread that's full of sodium bicarbonate, what kind of alkalosis do I get? Metabolic. Yeah. All right. So here, when the bicarbonate to CO2 ratio falls below, as soon as they say below, it's what? Acidosis. Or when the ratio is greater than 21, it's alkalosis. So if it falls below, it's acidosis. If it goes above, it's alkalosis. Respiratory acidosis, number one. What do you want to think about that ratio? Did it go below or above 20 to 1? It's below 20 to 1. The second thing, since it's respiratory, what caused it? The lungs. So what chemical are you pointing the finger at? CO2 changed. If the CO2 changed, it's respiratory. So in that situation, CO2 is increasing, right? So the CO2 is raising in the body. Is this written out in your notes? I don't remember. Okay. Okay, and then things that cause it. One cause is hypoventilation. You're decreased breathing. You're holding your breath too long, right? Another good cause would be some diseases. What lung disease do we say that the air stays in their chest too long? Asthma, emphysema, right? So chronic emphysema is a perfect example. They're holding too much CO2 and they're trying to hold the oxygen in, but they get stuck with the CO2 also. So emphysema is a really good cause of good. It's a cause. It's a cause of respiratory acidosis. And then if it's your lungs that are broken, how are you going to compensate? What's the first thing that's going to try and compensate? You're going to try and buffer acids. You're going to try and neutralize or buffer the acids so that it lowers.
Acidic.
Yep. Well, actually, yeah. It lowers the free acids. I'm getting it. What?
What was going to be done?
Any of those four things before, depending on what the cause was. Yeah.
Recover it. Or like ammonia and stuff.
Yep. So the chemical, first you're going to try and buffer or bind up the acids. Can the lungs fix this?
No.
No, because the lungs are what are broken. No compensation from the lungs. So what has to try and fix it now? The kidney. What's the kidney going to do if you're in a state of acidosis? What can it do? It's going to make you pee out more acids, right? What's going to make you keep more? Bases. What's the base? Bicarbonate. So it's going to try and make you lose more acids, secrete more acids, and it's also going to make you retain or reabsorb more bases. So that's the big picture. You want to think about when they say respiratory acidosis, well, what's the cause? First you think of the lungs. So what are they accumulating? CO2. What would cause you to accumulate CO2? Holding your breath, slow breathing, yep, hypoventilation, anything that slows your breathing. And then you just think exactly the opposite. So with respiratory alkalosis, it's the lungs that are broken. It's alkalosis, so what happens to that proportion? Does it go above 20 to 1 or below 20 to 1? It goes above 20 to 1. Yep. What chemical is to blame? Respiratory alkalosis.
CO2.
It's CO2. What are you doing with the CO2 then?
Increasing it.
You're losing too much CO2. So hyperventilation.
Right. Breathing too fast. Anything
So
like
why are they trying to get them to breathe into a paper bag, not a plastic bag? Why are they trying to get them to breathe into a paper bag? They're trying to keep the CO2 in, right? Because they're breathing too fast, they're blowing CO2 out, but if they're rebreathing that CO2, they're bringing it back in. Unfortunately, their oxygen concentration is going down, so depends on who you talk to. They try to kind of sway away from that anymore. So think about it. How do you fix respiratory alkalosis? What's the fastest way? You want to free up or bind acids? You want to free up. You want to liberate the acids, right? Can the lungs fix this? Nope. It's the lungs that are broken. The lungs can't fix it. So can the kidney do anything? Yep, what can the kidney do? Kidney can make you stop secreting, exactly. It makes you stop secreting acid, right? It makes you start secreting the base, bicarbonate. Yep. So it's going to try and conserve as much hydrogen as possible. It can't reabsorb it, just stop secreting it. And then it's going to try and make you secrete or excrete more bicarbonate. Is this and just this part the only thing that's missing in your notes? Just this up here and this? Okay. All right, so metabolic, you know, it's what causing it? It's anything but the lungs that are causing it. If it's acidosis, what happened to that proportion of 20 to 1? High or low? It's lower. What's the chemical you're pointing a finger at? Bicarbonate. So when they take an arterial blood gas, you'll see the HCO3 negative, you'll see the CO2, and you'll see a pH on those. You also see oxygen, but that's insignificant right now. So if their pH did what? Did it go below or above 7.4? It went below 7.4. It's acidosis. What are you going to see change significantly? The CO2 or the bicarbonate? The bicarbonate, right? So the bicarbonate did what? Did it go up or go down?
Down.
It went down. Remember, if you lose bases, the acid becomes more powerful. So it causes things like diabetes mellitus. So they have a fancy name for those people. It's called diabetic ketone acidosis. DKA, right? And I mentioned this earlier, strenuous exercise can do it. What acid are you accumulating here? Lactic acid. And you're also kind of accumulating CO2, but are the lungs working? Yeah, the lungs are working, and they're trying to do what with CO2? Get rid of it, blow it out. You're going, breathing heavy. What GI tract problem would cause metabolic acidosis? Let's see if you remember.
GI tract problem?
Yep. What caused you to retain too much acid?
Oh,
Diarrhea.
yeah.
So diarrhea makes you lose water, makes you lose base, right? So you're losing too much bicarbonate, which means you retain too much acid. So diarrhea would be a good example here. Okay. How is your chemical buffer going to compensate? What's it going to do? Free acids or free acids or bind acids? It's going to bind them to try and bind up the acids. Can the lungs work in metabolic acidosis? Yes, they can. What are they going to do? Breathe heavier. Why are they doing that? To blow out CO2 that takes the acid with it. Can the kidneys ever work in metabolic acidosis? They can, unless it's the kidney that's broken, but they can work. So let's say it's lactic acidosis, metabolic acidosis, right? What would the kidney do?
I have a question. When you said that it would make you breathe slower, but to get rid of that CO2, isn't that what you said?
Breathe faster.
Breathe slower, and I was like, I thought you.
Nope, breathe more, breathe out more. So with the kidneys, as long as the kidneys aren't the cause, what are the kidneys going to do to fix this? You're going to secrete acid and retain bicarbonate. So, yeah, you're going to retain the bicarbonate and you're going to start secreting more acid. Retain bicarbonate, secrete acid. Right, and then the last one, metabolic alkalosis. What's your problem? Higher or lower than 20 to 1? It's higher than 20 to 1, right? What's the problem if it's metabolic alkalosis? What chemical? Bicarbonate. What's it doing? Too little or too much?
Too much.
Too much. Yep, so too much bicarbonate. And then causes vomiting. Why would vomiting cause alkalosis?
Because you're all that stomach acid.
You're losing stomach acid, right. So if you're losing acid, then the base accumulates in your blood. And then ingesting alkaline drugs like was brought up earlier, all that alkaline covering and stuff, you're absorbing all that stuff into your blood. It's not because of the lungs, so it's anything else, it's metabolic. And then how will the chemical buffers handle metabolic alkalosis? What do they do to acids? They're going to free. They're going to liberate the acids. Can the lungs help here?
Yes, I mean.
Yep, the lungs can help. What are the lungs going to do in alkalosis? They're going to slow their breathing. They're going to slow their respirations. They're trying to do what? Keep CO2, which keeps the acid, right? And then, whoops, I flipped too quick. Go back. As long as it's not the kidney, can the kidney help it? Yes. What's the kidney going to do to the bases? Your alkalosis, your blood's too alkaline. You're going to excrete the base, right? And are you going to reabsorb acid? No. Why are you not reabsorbing acid? Because you can't. What are you stopping? You're just stopping secreting acid.
So what did the kidney do with lactic acid?
Urinate it out.
Acid?
Yep. So that gets filtered, it goes into the tubule, and you just don't reabsorb it, right? But in this situation, you're jumping back with lactic acid or metabolic acidosis. But with metabolic alkalosis, what are you going to do with acids? You can't help but stop, or you can't help but filter it. So you have to keep filtering them, but you can stop secreting them. You can just stop secreting them. Yep. So if I were to ask you a question about these acid-base imbalances, if a person has metabolic acidosis, the body will compensate in all of the following ways except what? What's the only thing it can't do? So metabolic acidosis, what's the cause? Anything but the kidney, or anything but the lungs, right? So it could be the kidney, it could be the muscles, it could be anything. So will the chemical buffers bind hydrogen in acidosis? Yes, they're trying to neutralize them. Will the respiration rate slow down in acidosis?
No, it's heavier.
What happens if your respiration rate slows down? You retain CO2, which retains acid, which does what to acidosis? Makes it worse. Yeah, so that one you can't do. Reabsorb bicarbonate from the urine. What's the bicarbonate do? Neutralizes the acid. And number 4, secrete acid. Can you secrete acid? Yes, you just can't reabsorb it. How about this one? If a person's hyperventilating, it could result in which of the following? What makes you say respiratory? Because it's the lungs. So you automatically know it's respiratory. You can get rid of 1 and 2. What's going to happen? If you're hyperventilating, you're doing what? You're breathing too much out. So what are you breathing too much out? CO2, which is losing acid, which makes you alkaline. Yeah. There they were. Next topic is energy balance. Energy, you want to think of things like calories. And we've talked about this a little bit when we talk about muscles too. And we already know this, that ultimately most of the food you eat is converted to heat. Remember, about 75% is lost as heat, and less than 25% is used as work. Okay? The energy input is the stuff you eat. Energy outputs, any type of work that you burn. External work is moving muscles to move you through space. Internal work is biochemical reactions. When you're moving enzymes, when you're moving all of the other things inside of a cell, those are biochemical. Okay? But that biochemical stuff is not technically work if you're a physics type of person. Right? And then food energy ultimately converted to heat. Right? And then 50% of the energy nutrient molecules are transferred to ATP, and then 50% lost as heat. And this is like the best you'll ever get. Metabolic rate, you kind of looked at this with Fit Day, but your metabolic rate is how much energy you spend to stay alive. And technically that's called basal metabolic rate. Just for you to stay alive and do your regular chores through the day is your basal metabolic rate. On Fit Day, when you did that, you were looking at it and it said if you had a strenuous lifestyle or a sedentary lifestyle, based on that, your basal metabolic rate was anywhere between 2,000 and 3,500 calories that you burn just by being alive every day. That's BMR, basal metabolic rate. Right, energy output has to equal energy input, and that's called what balance? Homeostasis or stable balance. If you're eating more than you're burning, it's what balance? Inputs more than output. It's a positive balance. Is that so positive when you're getting fat? Negative is when you're burning more than you're taking in. That's when you're on a super diet plan or you're an anorexic. So not always a good thing. Depends on what you want to happen. All right, so food intake is controlled primarily by the hypothalamus, which is what F? Whoops.
Food.
Oh, why'd that jump? It's jumping all over the place. All right, hold on a second. I don't know where we were. There it goes. Okay. So it's the feeding of the 4 F's. And then appetite centers, when we talk about the appetite center, those are the parts that make you want to eat food. Satiety centers make you feel satisfied, which makes you feel full. Mine is clearly very broken. And there are a lot of inputs. We point at the hypothalamus, but the hypothalamus never actually has the food go through it. It has no idea. So it has to have inputs from the stomach, from basically the blood and all over the body, telling it, hey, you've got plenty of blood sugar, you've got plenty of food in the stomach, you've got plenty of food in the small intestine. We even talked about one of those chemicals that you release from the stomach when it's full. It dumps it into the blood and it goes to the body and makes all kinds of things stop. Anybody remember what that hormone was? Somatostatin. Yep. Right. So the first of the hormones you need to underline is called leptin. So adipocytes or adipose cells, they release, when they get full, they start dumping this hormone called leptin into your system. So what is it telling you leptin's going to do? Make you feel hungry or make you feel full? Full. When your fat storage gets full, it releases a chemical that goes to the hypothalamus that says, stop eating, man. And it's called leptin. One of the things that they think is leading to obesity is that people are becoming leptin resistant, which means that hormone gets to the brain, but what's going on? The brain ignores it. Yep. And we just keep eating. All right, the part of the hypothalamus is called the arcuate nucleus. It's a little area of the hypothalamus. That's what, if you have a hormone, what's a hormone have to bind to? A receptor. That's the part of the hypothalamus that has the receptors for leptin. It comes up here, it binds and tells the hypothalamus, stop eating. Right? If there's no leptin bound, how does it make you feel? Not full, which means you want to eat. It makes you feel hungry. Right? The next of the hormone is called neuropeptide Y. This is an appetite stimulator. This makes you eat. Yep, so it comes out and it tells your body start eating, and it also tells your body stop burning calories, quit wasting energy. Take it in and stop burning it. What's that going to do to your weight? It's neuropeptide Y. Make you fat. The next hormone is called a melanocortin, and this makes you feel hungry. So what's the melanocortin going to do to your weight? Make you lose weight. Yep, so it decreases your food intake. It makes you want to eat less. What other hormone works with melanocortin? Leptin. This area is a really good transition into like hormones, because it's rare that you find one hormone that's like all doing the God hormone. There's always a group of hormones that work together or a group of hormones that oppose each other. Do you have a question?
Yeah, so instead of all of these ways to lose weight, leptin and things like that, why have they not come up with?
They could give you a drug that acted like leptin, but what if you don't have the leptin receptors? Doesn't make a difference. Yeah, this is a tricky thing about drugs, is we know all these drugs, we know all these pathways that we can affect, but if it's a chain of dominoes and there are 20 dominoes in that chain, if we give you a drug that affects one domino, it might not be the right domino. We may have just screwed the whole thing up. And
So are there any drugs out there for someone
there are. So there are drugs that are leptin blockers for people that have anorexia that can take and they gain more weight. There are also things that act like leptin, but at the same time, if you give them this leptin thing and they have no receptors, it does nothing. So, yeah. And if they just created it in the last 10 years, you wouldn't have even heard of it because of all the processes that have to go through for legalizing your drug.
The melanocortins
Yep.
make you feel hungry or full?
They make you feel, it says decreased food intake. What's that mean?
They make you feel full.
Full, which works with what other hormone that makes you feel full? Leptin. Yep.
Okay, you just said hungry, so I got confused when you said it.
I did say hungry?
Yeah, so I was like, wait, what?
Sorry. Yep.
Okay, so it's full.
Melanocortin and leptins, they both make you feel full.
Okay.
They don't have to work together. Yep, they can work separately. And I'm going to show you a pathway in a second. All right, so leptin, what it does is it comes up here, it activates that receptor for leptin, but it also binds or inhibits neuropeptide Y. Why would it want to inhibit neuropeptide Y? Because they work against each other, right? So leptin's like a bully, and it gets in here and shuts off neuropeptide Y so that it and melanocortin can win. That's another principle of drugs. That's why a lot of times when people take one drug and then they get put on a second drug, that second drug will actually affect the first drug because they don't always work together. Moral of the story is take care of yourself so you don't have to be put on any medications. So here's the pathway. Adipocytes dump the leptin into your blood. It's a hormone, right? Goes through the blood, goes up to the brain, and it stops neuropeptide Y, and it helps turn up melanocortins. These two work together. The melanocortins are going to make you feel full. The neuropeptide Y was going to make you feel hungry, but can it work now? Nope. Okay. So then these two hormones actually have another hormone. Like I said, a chain of dominoes, one after another after another. So the melanocortin is going to go over to this next hormone and shut off this thing called orexin, which makes you feel hungry. What's interesting is that cannabis activates the similar receptors to orexins, which make you feel hungry. I always see orexin, I think Oreos. Because every time I see an Oreo, I feel hungry.
Maybe that's why they named them that.
Maybe. So orexin makes you feel hungry. Melanocortins will shut it off. What's neuropeptide Y going to do to orexins? Turn it up. Because now they both work together and they're more powerful together. They're in the hypothalamus, so the lateral, and you don't have to worry about the part unless you really want to. They're listed up here. It's from the lateral hypothalamic. These are just pathways in the hypothalamus. Tick, 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 tick. Just dominoes that flip one after another. Yep. And then neuropeptide Y, since it's turning on orexin, it's going to shut off orexin's enemy, corticotropin. Right. Since melanocortins want you to eat, they're going to turn on, since melanocortins want you to stop eating, they're going to turn on the corticotropin. So this whole side of this pathway is trying to do what to your appetite? Shut it off. This side of the pathway over here is going to try and make you hungry. Yep. So if you're leptin, if you have lots of fat cells that are really full, but you ingest a little bit of marijuana because of your glaucoma, and then you get the munchies, right? Because this just totally bypasses and knocks the last knocks the last domino over. Told you, it always makes me think of Oreos.
Now when I say it, I shouldn't think of Oreos.
So this is what that pathway is telling you. So orexins, they stimulate food. Neuropeptide Y stimulates orexins, and melanocortins inhibit them. Corticotropin depresses or suppresses your appetite, so the melanocortins are going to stimulate those, where the neuropeptide Y is going to shut them off. And then the pathway we keep talking about is called the nucleus tractus salitaris. So it goes up from the brainstem, goes up into the hypothalamus, and it helps regulate your food. Have you heard of this last hormone, cholecystokinin?
Yeah.
What three letters did you just write next to it when you saw it? CCK. So cholecystokinin is made in the duodenum. Before we talked about it, it goes to the pancreas and makes you release enzymes to break down food, but it also goes to the brain and says, hey, guess what's going on down in the intestines? We're full, shut the hell off, right? So these cholecystokinin, they're going to make your pancreas break down that filling food, and it's going to go to the brain and say, stop eating for the love of God. We're so full down there. There's so much fat in our intestines. Please stop that. It's the pathway between the brainstem and the hypothalamus, and that's the pathway we keep talking about.
So
It's just the pathway.
CCK just says we're full, stop bringing you food?
CCK says, yep. It tells the brain quit eating. It tells the pancreas start breaking this food down, which we talked about back in digestion. Okay, so a hormone made by adipose tissue that suppresses appetite would be, how about number 4? Is it the melanocortin? Melanocortin suppress appetite, right? But they're in the hypothalamus. How about this leptin? Where's that? That suppresses food intake. It's made in the adipose tissue. Yep, so that's the right one. What do neuropeptides and orexins make you do? Give them the munchies. All right, so here are all the things that affect the hypothalamus, so your food intake. You can see gastrointestinal distension. Think cholecystokinin, which is down here, and the duodenum. Lots of food. It's going to make you do what with your appetite? You're packed with food already. It's going to make you hopefully stop eating. There must be something in Chinese food that shuts this stuff off, right? And then glucose. So if you're increasing your glucose use, it's going to shut this pathway down. If you increase insulin, it's going to shut this pathway down. Because when you have high glucose in the blood and you have high insulin in the blood, it's telling you have way too much food coming in, way too much sugar in the blood. Stop eating. Over here, this is psychological. If you smell or taste food, that can have a psychological effect. Have you ever put something in your mouth and it's so slimy you go, and you lose your appetite? So it inhibits. You ever put something in your mouth and it tastes or smells delicious? Makes you want to eat more chocolate cake. Right? Stress and anxiety. You ever had a day where you're so stressed you can't eat? You ever had a day where you're so stressed you just have to have some chocolate cake?
No.
Absolutely. Right? And then the amount of available food. So just seeing piles of food can be, you're like, there's no way I could eat all that, so I don't even try. But the same thing when you see McDonald's and you think, Shamrock Shake, that sounds pretty good. Even though you weren't hungry, now suddenly you're hungry.
What about
So there's a lot of multiple factors.
Getting close to grocery time and you don't have a lot of that stuff, you're like all of a sudden really
Yeah,
hungry.
eat some Oreos, then go shopping. Don't
Maybe
go shopping on
you
an
go
empty
to the
stomach.
grocery shopping and you have all this stuff, like you're like all of a sudden not hungry.
There you go.
Too much
So-
to choose from.
Not hungry. And then obesity, the disorder. So the disorder, there are lots of causes. You can see them. So the first one, breaking that leptin pathway, which they think is a common problem. Those people that they regulate they regulate their diet, but they're always hungry. Maybe it's the leptin pathway. Lack of exercise can cause obesity because you have a what balance? Positive or negative balance? Positive balance. The fidget factor, I love this. So the fidget factor, you ever know the person that's constantly fidgeting? They're constantly moving. That's like my whole family. At the holidays, we don't actually pass food anymore. It's because everybody's bouncing their leg, the table shakes, and the food vibrates around the table. So as it's passing by, you just take a scoop of the potatoes. Yep. They call it non-exercise, it's neat, non-exercise something thermogenesis. Oh, non-exercise activated thermogenesis. You're burning calories, you're burning heat, but you're not exercising. Yep, when you're shaking leg.
There's a medicine for shaky leg syndrome.
Those people that are just, they call them high metabolism. They're kind of like constantly fidgety. And then number 4, differences in extracting energy. They think based on the part of the world that your ancestors came from, either you had an abundance of food, which you didn't have to extract a lot of calories because it was already there. And then there are the places that they barely had any food. So if you get an apple in you, you better extract every damn calorie out of it, right? So if you take something that's good at extracting calories and you put them in a McDonald's, what's going to happen to them? They get fat, right? Because they're absorbing every calorie they possibly can. Whereas people that came from a very abundant food population, they don't seem to gain any weight. Nope, that's the next one, energy extracting. Okay. Huh? Difference. It says a difference in the fidget factor. If you don't fidget much, then you don't burn calories and you gain weight. Yeah. And then hereditary tendencies you can see above. So did you inherit that fidget factor? Did you inherit the ability to extract calories really well? My mom could always eat like a whole box of macaroni and cheese, and she never hit 100 pounds in her life. So yeah, she was really good at the fidget factor and not extracting calories. I wish I got that. Number 6, development of an excessive number of fat cells as a result of overfeeding. You ever heard that once you gain the weight and you lose it, it's easier to gain it back? Yep. You've already got a pantry bill on your house. Why not just fill that thing again, right? So when you build these extra fat cells, they just shrink down, but they're ready to be refilled again. When you built them the first time, you put calories into building those things, but now they're all built.
How do you make those extra fat cells?
Just by eating too much. Yeah, if your body doesn't want to lose those calories that you worked hard to get in, so it just starts building storage units for it, and you just get fatter and fatter and fatter. And then when you lose it, then they're always there, and they're ready to boop, plump back up again. Liposuction. It's the only way to get rid of them. Yep. Number 7, the existence of certain endocrine disorders like thyroid issues would be a good example. Hypothyroid turns down your metabolism, you store calories better, you don't burn them so easily. Number 8, abundance of convenient, highly palatable, energy-dense, relatively inexpensive food. Really? So yeah, just having McDonald's in every corner can help you gain weight or be obese. Number 9, there's a possible virus link, and what's interesting is they think that the common cold has a link that causes obesity. They think there's stuff in the common cold that when it gets into you, it actually possibly blocks the leptin pathway or causes other issues.
What's a faux pas?
Is it?
Yeah.
Right. And then, of course, anorexia nervosa, and what's the other one that usually is associated with this too? Bulimia nervosa. Anorexia, and if you've ever taken a psych class, they associate with things like anxiety and control. People that have lost control in their life are more tendency to become anorexic because the only thing you really have control of in this world is you. Yeah, what you control about you. So they get satisfaction or happiness out of controlling their diet. They can see something delicious that everybody else is enjoying, and they feel good because they say no. And unfortunately, they say to the point where they have a what balance, a positive or a negative balance. A negative balance, and they're losing more calories than they're actually taking in. Where bulimics, they eat whatever looks good, and then they feel regretful. They lost control, so their only way to fix that is to vomit or laxative or exercise it out of them as fast as they can. And then the last section, which we'll just barely have enough time to talk about, is temperature regulation. I'm telling you the keys here. What's the organ that regulates your temperature? Hypothalamus. Remember freezing. another F. Your body's core likes to stay right at about 100 degrees, and that's just a nice round general number, 100.000. That's your core. Does your body's surface ever change? Yeah. If you're outside, your body temperature on your surface can actually drop down to around 60 degrees as long as your core stays consistent with your internal organs. So what happens when you go outside? Your skin turns pale because you're squeezing all that hot blood where? Down into your core to keep it warm. Your hypothalamus doesn't let you go beyond roughly 0.01 degrees in your core. So if you have a 0.01 degree change, you drop by 0.01. 1/100th of a degree, your hypothalamus makes you do what? Your body temperature dropped. What do you do to warm up? Shiver, right? What's going to happen to the blood vessels at the surface of your skin? They constrict to push that warm blood back down to the core. So very sensitive to change. So central core, like I said, about 100 degrees. Your outer shell can go anywhere between 60 degrees all the way up to 104 comfortably. At 104, you're not losing heat fast enough, so then it stays inside, and what's it doing to you? Cooking you. And normal variations, there are a lot of things that cause, like sleep. In the sleep, you change roughly about up to 2 degrees. So you'll drop down 2 degrees, you cool off a little bit, and then when you wake up, that's why in the morning a lot of times you're kind of cold, and you're like, ugh. And you start moving around, and you're fine. And women around menstruation, we'll talk about this with progesterone and estrogen, but progesterone actually makes your body temperature spike. So when progesterone spikes out, it's a sign of ovulation, and that's how they measure the temperature thing to know when they're fertile. And then number 3, during exercise, obviously, when you're moving your muscles a lot, you raise your body temperature, and then extreme temperatures like at the top of Mount Everest or in hell, wherever. All right, so extreme temperatures can change this. Just seeing if you're still listening. So heat output, when you're putting heat out, the way you do it is you do things like what? How do you get rid of heat? Sweat. How else do you get rid of heat? Pant, breathe heavier. Exactly. So sweat, breathe heavier. You will actually instinctively seek cooler environments. You think, oh man, I gotta get to the shade, but in reality your body's making you go there. It's the same with when you're losing. So if you're too cold, you want to do what? Put on something warmer, right? Have you ever, and this tells you instinctive, have you ever stayed at a friend's house on their couch and it's always freezing in their living room, right? And then you wake up and you have a rug on top of you?
Yeah.
Okay, good. I thought it was just me. But, right, in your sleep what you did is you were asleep, like not even conscious, and you look for anything that would keep you warm. So you grab the rug off the floor and you pull up over you. Right? Or you cover yourself in pillows. Or you find somebody's coat that's laying next to you and you cover up on it. Those are instinctive movements. When you're hot outside and you want to peel off your clothes, look at little kids. When they're hot outside, what do? They take everything off, right? They're just comfortable. It's because you instinctively know that when you're hot, you want to get rid of this stuff, right? So you have to maintain that balance. If you take in too much heat, it's called a what balance? Take in more than you're getting rid of, it's positive. If you make more than you can get rid of, it's called positive. If you lose more than you can make, it's called negative. Yeah. So here are the 4 processes: radiate, conduct, convection, and evaporate. Radiation is through electromagnetic rays. Sun is a perfect example. Do you touch the sun?
Yes.
No, but can you feel its effects? Yes. It's because of radiation. And you know that you can actually get overheated because have you ever heard of a radiation burn?
Yeah.
Right? How about conduction means you actually have to be touching the thing. If you sit down on a cold seat and you're like, whoa, what's happening with the heat? Is it going into you or going out of you? It's going out. You're a high concentration of heat. The seat is low concentration of heat, so it goes out of you. When you hold a snowball, what happens?
Your heat goes into the
You
snowball.
conduct your heat into the cold snowball. You lose the heat. So actually touching things. If you put somebody in a warm coat, that's conduction. You're putting the warm coat into them. Like a heating pad. That's a good example. Convection means moving by air current or water current. Convection. So where have you heard of convection? In an oven. What's the only difference between a normal oven and convection? It has a fan. Yep, that's the only difference. The fan blows the heat around to help heat things evenly. If you were in a room that was 110 degrees, if the room were 110 and you put a fan on you in that isolated 110 room, guess what you just did? You're cooking yourself by convection. Yep.
Wait, what? Fans never just
Nope, it just distributes the heat. Yeah. And then the evaporation is when you take it from water and the water pulls away the energy as heat. What are you doing for evaporation? Sweating. Yep, the heat goes into the sweat evaporates and takes the heat away. So the next time you're at a gym and you're sweating all up like crazy and you're wiping sweat off, you're actually defeating the purpose, right? You need to actually like just strip down to nothing and air dry.
get right then. That's when you
Yep. In fact, if there's somebody that's next to you and they look like they're really hot and they're not sweating very well, just rub them. Rub your sweat all over them. Share. So these are just picture examples and they're all in your text. So if I ask you the transfer of heat between objects of differing temperature, they're in direct contact, that's conduction. And then, of course, you know this, the hypothalamus is what controls it, and it's off. It only lets you go off by 1/100th of a degree before it starts freaking out. The receptors, you have peripheral receptors out here in the periphery, and you also have central receptors that detect the temperature in places like the brain and internal organs. So this time central doesn't mean just the brain, it means the internal organs too. So that your core doesn't cook. Alright, if you get too cold, shivering generates heat, so it's creating the heat. And what it does is oscillating 10 to 20 times per second. So you're actually twitching. When you see that twitching, it's actually moving that muscle 10 to 20 times every second. Okay. Non-shivering happens primarily in babies and animals that hibernate. It's a chemical reaction. They actually burn. You ever had one of those things that you break? It's a plastic packet and you break it and it starts getting hot? That's thermogenesis, but it's not actually movement. It's the same idea. Your body, you have certain stores of fat they call brown fat when you're a kid, that as you get cold, you start releasing this heat in your body to warm your blood up. So a bear doesn't have to shiver to stay alive in that cave. You already know this. How long before you lose it? I don't know how long you keep your baby fat. Yeah, it fluctuates. There you go. Alright, so when you're trying to lose heat, what do you do to your blood vessels at the surface of your skin? Open them. The heat goes out through evaporation, convection, and it drops your temperature. If you're trying to hold in heat, what do you do to those blood vessels? Constrict them and you look pale. Yep, it's technically 2:31, but I have, 2 slides left, so if you want to leave, you can. I'm just going to do this for the recording. So, hypothalamus stimulated coordination between heat production and loss. It's the hypothalamus. That's the third time you've seen that. And then the coordination to cold exposure is in the back of the hypothalamus. Coordination for heat is in the front. Right? So anterior versus posterior. So response to cold exposure by the posterior hypothalamus is going to make you want to do what? If you're cold, you're going to try and warm up. You shiver. You try and cover up involuntarily. You start burning brown fat if you've got it. You're trying to create heat. If the front, the anterior part, turns on and says, man, you're too hot, what are you going to start doing? Vasodilate, breathing heavier, stripping your clothes off to nothing, right? And you're trying to cool off. So if you were asked a question like this, if you go outside during the winter in short sleeve t-shirt and no coat, how does your body compensate? Outside in the winter in a short sleeve t-shirt, shiver. Yeah, if you sweat, you're losing more temperature. You vasodilate, you lose more temperature. If you lay down in the snow naked and do snow angels, yeah, that's not a great idea. Right. Okay, oops, I already said this. So in the anterior portion, this is the side that makes you want to cool down. So I already told you all these different things. So if you go outside in the middle of the summer, it's over 100 degrees, what is your body going to do to compensate? Are you going to start shivering? No, that generates heat. Are you going to do postural change and roll up in a ball? No, when you're wet, you roll up in a ball. You're cold. Have you ever woken up in the middle of the night and you're like in the fetal position? Instinctive. How about you're going to instinctively go to wear a black wool sweater? No. Not a great idea, right? So is your blood going to vasodilate? Yeah, you open it up. It's like a radiator in your car. You use that to cool off the engine. Your blood vessels are radiators. They're cooling off your blood. And then the last thing here, fever. A fever is a good process to an extent. A fever is when the hypothalamus's temperature is reset just a couple points higher. The hypothalamus is saying, you know what, there's bacteria in our body. The best way to kill it is to cook it. So it goes from 98 degrees to 99. And then from 99 to 100. And if the bacteria is still there, it goes to 101. If the bacteria is still there, 102. If it's still there, 103. If it's still there, 104. Will it stop? Not until the bacteria is gone, right? So when it starts getting dangerously high, you need to start doing external regulators because this fever can get out of control. But fever's for a good thing until it's uncontrolled. And it's these endogenous pyrogens that do it. What's a pyro? Somebody loves fire, right? So it's a fire generator that does this. And it's because of microbes like bacteria that does it. When you get a fever, how do you feel right away? You feel cold. How do you look? Pale, right? When you have a fever, you look pale, clammy, cold. Why? Because your hypothalamus is saying you're freezing. Even though your temperature is 101, it's saying you're freezing, so what's it trying to do? Create more heat. And then when you, quote-unquote, break the fever, what happens? The set point went from 103, where you're at, down to 98, and the hypothalamus goes, why are you so hot? And what's it going to make you do now? Sweat. Throw all the covers off. You're sweating like crazy. You're breathing heavy. You're like, oh my gosh, just cool me off. When you start a fever, you get cold because your hypothalamus' set point goes higher and your body's trying to get up to that temperature. When you break the fever, the set point goes down and you're already at the high temperature, so you're trying to cool it back down. That confuses a lot of people.
Yep, me.
Right? So when you have a fever, how come you shiver? The wording's a little weird, but if you shiver, it's because you're trying to lose heat. Shivering generates heat, right? Cross that one out. If you're shivering, are you trying to produce heat and reach your new thermostat point? Yes. When you have a fever that's at 102, but your body's only 100, you start shivering to try and bring it up to 102. You're trying to generate heat. Okay. And then hyperthermia. I forgot this was on here. But hyperthermia is not healthy ever. If you exercise and you get too hot, it's bad. People that run marathons out in the sun in the desert, not a great idea. If you get heat stroke, by the way, is one word you want to write down, heat stroke. Heat stroke means that your hypothalamus has shut off. It's gone. Is it going to help you regulate temperature anymore? Nope. Does it mean that your temperature is fixed? Nope. It means that they stop compensating. Their blood vessels go back to normal, so they're not red anymore. They start going to regular temperature. They're not sweating like crazy anymore. Their sweat starts decreasing. They're not breathing heavy, but are they cooled off? Nope. It's because their brain is cooking. Their brain's literally cooking. So when hyperthermia actually gets to the point where it's heat stroke, you're a goner. Right. Thanks for the extra 6 minutes. When we come back on Tuesday, what's happening? Test. Make sure you have lecture quiz number 10 done by then, and there is no homework number 10.
But the homework number 9 is.
Number 9 is due by Tuesday. Yep. So you should have number 9 done by now because we're actually completely done with it. But it's open till Tuesday. And digestion you should have already had done. Your urinary you should have already had done. So it's lecture number 10 that's due by Tuesday.
Wait, no, you said urinary was not turned in yet.
The quiz?
Yeah.
Oh, there's no slot for number 10? Okay, I need to remember to.
Urinary and this one are due Tuesday.
That's right. Homework number 10 is over. No, it's over urinary.
Oh.
Yep.
I have it in my hand. I do have a question.
So just make sure that everything that has to do with digestion, renal, fluid acid base is all turned in by Tuesday because we have the test.